Hello, everybody. Welcome back. Today we're going to be looking at Unit 9.8, which is on cell potential and free energy. So let's get started. All right, so let's remember that when we're talking about a galvanic, or sometimes they're called voltaic cells, a battery, that electrons flow through a wire from one side, one half cell, to the other half cell. And the reason that that happens is because you've connected two reactions that are an overall redox reaction, which causes, again, electrons to flow through a wire. And that's changing chemical energy into electrical energy. Well, that electricity that's flowing through the wire can be measured, okay? And the amount of electricity that's flowing through the wire, in chemistry, we call that the cell potential. If you are more of a physics-minded kind of person, you might call it the electromotive force. And that word force is sort of a little bit misleading. We can kind of think of it as the pull or the push that is moving electrons through the wire, but my physics friends tell me that it is in fact not a force. It's just a difference in potential from one half cell to the other half cell. But for our purposes, guys, you can sort of think of it that way, that it is sort of, even though it's not really a force, it's the, quote, force that is either pulling, you can think of it as a pulling the electrons through the wire. You can also think of it as a push. The electrons are being pushed through the wire. It really doesn't matter how you think of it. We are going to call it the cell potential, and it is measured in volts, okay? And I showed you a diagram of a galvanic cell in the last unit, and there was a voltmeter attached to that wire that is measuring the voltage, the cell potential, how much electricity is flowing through that wire. And in chemistry, we are going to use a variable, a capital E with a little subscript cell. On occasion, sometimes you'll see, instead of a nice printed capital E, sometimes you'll see it written like this. It's sort of this very fancy, almost cursive script E, okay, with a subscript cell. It means cell potential, and it is measured in volts. Now, each half reaction is going to have its own potential, and so we have to have what we call a standard potential. And I'm going to show you in just a minute a list of these half reactions, but a reaction that involves hydrogen, there's a half reaction we're going to see in just a moment, that involves hydrogen, and the potential of that particular reaction is called the standard cell potential because it has been deemed to be equal to 0 volts, okay? So you can see right there that sort of fancy script E, okay? That means potential. And I want to just refresh your memory on what that little degree symbol means right there, because all of our cell potentials are going to have that symbol. Remember, that means these are potentials that are measured under standard state conditions. That means all of the gases are at 1 atmosphere of pressure. Anything aqueous is at a concentration of 1 molar, and the temperature is 25 degrees. So, depending on who you are and you're watching this video, you should have available to you some sort of table like what you're seeing in front of you. It may be in the appendix section of your textbook. Those of you that are actually my students, I'm going to make available to you a big chart that has a whole list of different half reactions and their cell potentials, or their reduction potentials actually. And that's the way that these charts are written. If you look at the title of the chart, it says standard reduction potentials. And you'll notice, guys, if you look at all these half reactions, notice that for every half reaction, the electrons are on the reactant side. And if you look at, each substance from left to right, you'll see that its oxidation state is decreasing. All of these reactions are written as reductions. Okay, so that's standard. Any chemistry textbook is going to have a chart like this. They're always going to be written as reductions. Okay, so let's kind of get to know this chart. And it doesn't matter if you're using the same textbook as I am, it doesn't matter. All of the charts are written the same way. So where are the substances that are being reduced? Well, since this is a reduction table, we're looking at the reactants. So for example, the first half reaction in the chart, F2, fluorine gas, is the substance being reduced. In the next one, permanganate ion is the thing being reduced. In the next one, chlorine gas is the substance being reduced. Okay. Now, we're going to talk a little bit later today about favorability. Okay, remember, favorability just means which reaction is the most likely to occur on its own, most readily. So the question says, which substance has the most favorable reduction potential? Okay, I'm going to say something to you, and we're going to sort of flesh this out a little bit more later. But the more positive the potential, the more favorable that process is. Let me say that again. That's important. The more positive the potential is, the more favorable that process is. So this question, when it says which substance has the most favorable reduction potential, if you look at this chart, which one has the most positive potential? That would be fluorine. Fluorine gas in this particular chart is the most readily reduced substance. Okay, now if you'll recall, guys, a galvanic cell or any redox reaction has something being reduced, but it also has something being oxidized. So how do you, is there another table that has oxidation half reactions? No. How do you turn a half reaction that is written as a reduction, how do you turn that into an oxidation? You flip it around. Okay, you reverse the sign of the arrow, you flip it around. So that first reaction at the top, if I flip it around, would be written as 2F minus yields F2 gas plus 2 electrons. Guess what happens to the reduction or the potentials when you flip a reaction around? It changes sign. Okay. So this question says, where are the substances that are being oxidized? Well, they're on the product side. Imagine you take everything that's on the product side in the chart in front of you and flip it around. Okay, so in the first reaction, F minus, if I flip the reaction around, F minus is the substance being oxidized. Which thing in this chart has the most favorable oxidation potential? Remember what I said earlier. The more positive the potential, the more favorable that process is. So I want you to imagine every reaction on this chart flipped around and all of the potentials opposite in sign. So I'm hoping that you were able to answer that solid lithium, not lithium ion, but solid lithium is the most favorable thing to be oxidized in this chart, because if I change the sign, I'm going to get positive 3.05. That's going to give me the most positive oxidation potential in this chart. Okay, so I just wanted to sort of help you get to know this chart a little bit because you're going to use it a lot. So let's bring this back to, let's unite talking about this chart, this reduction table with a galvanic cell. And let's imagine that we have a galvanic cell with this overall reaction taking place. The total cell potential, meaning the voltage that the voltmeter is going to read, the amount of electricity that I'm getting out of this galvanic cell, is the sum of the potential from each electrode, which means I'm going to look at my reduction table and I'm going to figure out the potential for each half reaction and I'm going to add them together. And that's going to tell me the total voltage that I will get out of this battery. Okay, so we have to look up the reductions in the table. If this were, if it's a question on the AP exam, guys, you won't have access to this table, but the questions will give you the reduction potentials that you need. So there's nothing to memorize. Now, of course, one of these half reactions is going to have to be flipped around because, as we said, a galvanic cell has one half reaction that is reduction. So that we can just pull right out of the table. We don't have to change it. The other one is an oxidation, and that one does have to be flipped around, and so we'll have to change the potential sign as well. Now, how do you know which half reaction is the one that you need to flip around? Here's how you know. If we're talking about a galvanic, or sometimes they're called voltaic cell, this is really important, guys. The overall cell potential will be positive. Okay, we are going to talk in two subunits, unit 9.10, we're going to talk about something called electrolytic cell, which are the opposite situation. But if it is a galvanic cell, the total cell potential must be positive. And that's, I'm going to show you an example. That's how we're going to know which half reaction do we have to flip around. So let's look at an example. It says, write a balanced cell reaction and calculate the cell potential for the cell using your standard reduction potential table. You can use the one in the back of your textbook, or if your teacher has provided you with one, you can use that. And you might say, well, wait, aren't you already giving us the balanced cell reaction? And no, I'm not. This is what I would call a skeleton equation. It might look balanced, it's not actually charge balanced. So here's my thought process. Okay. First thing I'm going to do is I'm going to use my reduction potential table and I'm going to find these two half reactions. The first one I'm going to try and find is any half reaction that involves chromium plus 3 and chromium plus 2. They may or may not be in that order, doesn't matter. You want to find a half reaction that involves those two species. And in fact, we find it and it looks like this. And I'm literally just copying straight out of my reduction potential table. And out to the side, it tells me that the potential for that half reaction is negative 0.41 volts. Okay, I didn't change anything, I just copied it straight out. Next thing I want to do is find the other half reaction. Find the half reaction that involves magnesium solid and magnesium plus 2. It may or may not be in that order. That's okay. We're just going to copy it straight out of the table, and this is what it looks like. Okay, and out to the side, it says that this potential is negative 2.36 volts. Okay, now, these are both written as reductions, and obviously I know I'm going to have to flip one of them around. Now, looking at the skeleton equation, you may already know, okay, we're going to have to flip the magnesium equation. And you're right, because if you look at how it's written, magnesium solid is on the reactant side, and right now it's not. And so, yeah, I know that that's the one that I need to flip around, but here's another way you would know. Okay, let's say you weren't given this skeleton equation at all, and you were just told, okay, the galvanic cell is going to involve these two half reactions. How would you know which one to flip? Remember what we said. If it's a galvanic cell, which that's what we're doing right now, the total has to be positive. Okay, so I know I have to flip one of these, and whichever one you flip, the cell potential or the reduction potential is going to change sign. And then we're going to add these two potentials together. I know that the magnesium one is the one I have to flip because this will then become a positive 2.36. And when I add these two numbers together, that's going to give me a positive total. If you made a mistake and flipped the chromium reaction around, that potential becomes positive 0.41, but when I add it to negative 2.36, that would give me a negative potential, and that's not what happens in a galvanic cell. Okay, so I am going to alter this reaction and write it properly. Okay, and then that becomes positive. Okay, now we're not quite finished here. Think way back to when we did balancing redox reactions. Remember, guys, that before you add your two half reactions together, the number of electrons must cancel out. They must be the same, and right now they're not. The chromium half reaction has 1 electron, magnesium reaction has 2. So what are we going to do? We're going to multiply this top equation times 2. Now this is really important. Focus here. I just multiplied everything in the chromium reaction times 2. Ladies and gentlemen, I am not going to change that number at all. Cell potential, or any kind of potential, is not an extensive property. When I change the amount of reacting material, it does not alter the number of volts. So I'm going to leave that negative 0.41 just as it is. But you'll notice now that the electrons cancel out, and they have to. So here is my balanced equation. So it looks very similar to the skeleton equation that we were given, but now it is charge balanced. And now I can write the word cell because it's for the entire galvanic cell. And that's the cell potential I get. Okay, so that's the thought process. That's how you do these kinds of problems. So let's bring some things together here. Okay, if we want to give a complete description of a galvanic cell, usually you're going to be asked, just as we were a moment ago, to find the balanced cell reaction and calculate the cell potential. And if it's a galvanic cell, it's going to be a positive total. Okay. If it's a drawing, you may be asked to draw in an arrow indicating which way electrons are flowing. Okay. And you may be asked to identify which half cell is the anode and which half cell is the cathode, which we talked about in our last unit. But let me bring some things together for you. Remember The anode is where oxidation takes place, whichever half cell that is. Well, guess what, guys? Whichever half reaction you flipped is the anode. Why did you flip it? You flipped it to turn that reduction into an oxidation. So let me say that again. Whichever half reaction you had to reverse, you had to flip and change the sign, that is your anode. Okay. Oops. So what I would like for you guys to do is to pause your video here. I've given you all the half reactions, so you don't actually even have to look them up in your table. But for each of these, I want you to come up with the balanced cell reaction, calculate the total cell potential, and since there is no drawing, you can't draw electron flow, but I do want you to identify which half reaction is the anode and which one is the cathode. All right, let's see how you did. So we started the first one that was relatively simple, and you're given the two half reactions, and your job is to figure out which one am I going to have to flip. Remember, a galvanic cell needs to have a total positive cell potential. So in this first one, it ended up being that I was going to flip around the aluminum reaction, which I had to do that because I need an oxidation. The sign changes for its potential. The other thing I had to do, remember, you have to make sure that the electrons are equal so that they will cancel out. So I had to multiply that copper equation times 3. But remember, that does not change the potential at all. So that number remained unchanged. I add them to the potentials together, and I get 1.813. And there is my balanced reaction. And whichever half reaction you had to flip, you flipped it to turn it into an oxidation, and that is where the anode is located. Anode is where oxidation takes place, which makes the other one the cathode. The second problem, okay, was a little bit more complex just because it had more things in it. Okay, but that does not change the process at all. I was able to recognize that the manganese half reaction was the one I was going to flip around. But then I also noticed that in these equations, I had 2 electrons in the ozone equation and 5 electrons in the manganese. So I had to multiply the manganese equation times 2 and the ozone equation times 5. And I rewrote them a little lower down. And there are more things that could cancel out than just electrons. You'll notice that I was able to cancel out some of the waters and some H+ ions. Okay, so when you have these longer, more involved half reactions, sometimes there will be other things that you can cancel out. But again, since the manganese equation is the one I flipped around, I know that is my anode. The ozone equation was my cathode. My total cell potential comes out to be 0.56 volts. Okay. And of course, guys, let me just bring this back up again. If this were a free response question and maybe there was a drawing and you were asked to draw an arrow indicating which direction electrons are flowing through the wire, remember, electrons always flow from anode to cathode. So if this were, if this were a drawing, I would draw the arrow leading from the manganese half reaction side over to the ozone side. And let me remind you of one other thing. Both of these half reactions, I should say, neither one of them have anything in them that is solid. Remember, guys, these galvanic cells always have to have some sort of solid electrode. The manganese half reaction, everything is in aqueous form. In the ozone equation, both ozone and oxygen, those are gas gaseous states. So in both of these half cells, I would need to have an electrode made of either platinum or graphite because neither half reaction has something in the solid state. Okay, so let me just reinforce something that we've already talked about. So a galvanic cell is always going to have a positive cell potential. And let me bring this together with some things we've talked about earlier in Unit 9. A positive cell potential means a galvanic cell that is going to run spontaneously. So if I hook up all these half reactions, these two half reactions, I will get current flowing without me having to really do anything. Okay, it happens on its own. So let's look at some examples here of kinds of questions that you could be asked. Okay, and I want you to use your reduction table, okay, whichever one you're using. So let's look at this question. It says, is cadmium metal capable of reducing zinc plus 2 ion? So what I want you to do is find cadmium metal, cadmium solid, on your reduction potential table. And when you find it, you'll notice that it is on the product side. And that's not where we want it, okay? The way this question is phrased is essentially asking, will cadmium metal react spontaneously, favorably with the zinc ion? So cadmium metal being on the product side is not where we want it. So flip it around, and you'll notice that when you flip it and change the sign, the potential for that half reaction is positive 0.40 because I flipped it around. Now I want you to find zinc plus 2 ion on in your table, and you'll notice that it is on the reactant side, and that's where we want it, so we're not going to have to flip that one. And that half reaction has a potential of negative 0.76. So what do you get when you add negative 0.76 to positive 0.40? Do you get a positive number? The answer is no, you don't. So the answer to this question is no. Cadmium metal is not capable of reducing the zinc ion, or at least it's not going to happen spontaneously on its own. Okay, that combination would not be in a galvanic cell because we get a negative total cell potential. So let's look at another one. Will an electrochemical reaction involving iron metal and solid iodine, will that occur spontaneously? Okay, so let's look at our table and let's find iron metal. And actually there's probably more than one equation that has iron metal, and it actually doesn't matter which one you use. Okay, pick one of them, but no matter which one you pick, you'll notice that iron metal is on the product side. So you're going to need to flip it around. Okay, think about what happens to the sign. It's going to change sign. Again, no matter which iron equation you're looking at, when you flip that equation around, it's going to become a positive number. It's either going to be positive 0.44, it might be positive 0.04. It depends on which half reaction you're using. Again, it's not going to matter which one. Find iodine, I2, find it. When you find it, you'll see that it is already on the reactant side. That's a good thing. So we're not going to have to change that one, and its value is positive 0.54. So think about what kind of a total are you going to get when you add your numbers together? It's going to be a positive answer. So is this reaction capable of happening spontaneously? The answer is yes, because the cell potential is positive. Okay, let's do one more. Let me move that down. Is sodium ion capable of oxidizing aluminum metal. We'll find sodium ion, and you'll see that it is on the appropriate side. It's on the reactant side, so I don't have to change that one. And that has a potential of negative 2.71. Aluminum metal, however, is on the product side. I'm going to need to flip that one around, change the sign, and I get 1.66. When I add these two numbers together, I'm going to get a negative total. So no, this is not going to happen. Okay, so you may be asked questions like this in free response, and you would need to justify your answer by maybe showing some math and giving an explanation based on the fact that whether your cell potential is positive or negative. So let's bring some topics together. Okay, we have talked about Gibbs free energy in previous subunits. Remember, guys, the entire purpose of delta G is to identify whether a process is favorable or not. This equation that you are seeing in front of you links Gibbs free energy and cell potential at the end. Okay, it links those two concepts. Now, what about the other ones, those other variables? Okay, little n there is number of moles of electrons. Let me translate that for you. Think about what we've done in a couple of previous questions where we had to cancel out electrons. Whatever the coefficient was when you canceled out electrons on the left side and the right side, that's what you plug in there for n. Okay, so let me say that again. The number that gets plugged in for n here is whatever the coefficient is for the number of electrons that you canceled out when you added your two half reactions together. F is something called Faraday's constant. That number, 96,485, you do not need to memorize. It is on your equation sheet. Also, I should have said before, the equation up at the top here, also on your equation sheet. It's in the same neighborhood as all the other thermodynamic equations we've been looking at. Now, let's bring some concepts together here, guys. Let's review. When delta G is negative, that indicates a favorable process. Well, think about what we've talked about today. When the cell potential is positive, that also indicates a spontaneous process. And now these two things mathematically are linked. Think about it. Look at that equation in front of you. If if the cell potential, E, is positive, F is positive, N is positive, that's going to give me a negative delta G. And it will be favorable. Whereas if E is less than 0, negative, it's not going to be spontaneous because the delta G is going to be greater than 0. And as I said, in unit 9.10, we're going to look at what are called electrolytic cells. And you're going to see there that they, unlike galvanic cells, they have negative cell potentials. And we'll talk more about that in unit 9.10. So this is the last thing I'm going to ask you to do. This is a free response question that's going to sort of bring everything together here. So I want you to pause your video and see how you do with this one. All right, let's check your answers. So you have seen this diagram before, actually, but it's in a slightly different context because I'm not telling you anything about it. I'm not telling you where the anode is, where the cathode is, which direction the electrons are flowing. I'm not telling you any of that. All right, so your first task was to come up with the balanced equation. Now, at the top of the slide, you see this word voltaic, meaning galvanic cell. And remember, guys, a galvanic or voltaic cell must have a positive total. So that's going to help you to know which reaction needs to get flipped around. And as you can tell, it was the aluminum reaction that we had to flip around, okay? Which means the aluminum half cell is my anode, the iron side is my cathode. Determine the cell potential. All I had to do was add my cell potentials together. Remember, we had to change the sign of the aluminum reaction. And so I get a positive total, which I should, of 1.21 volts. Okay, next part says, does the concentration of Al3 plus in the solution increase, decrease, or remain the same as the cell operates? And if you think about what our balanced final equation was, okay, I said that the concentration of the aluminum ion will increase because as the cell operates, aluminum is being produced. It's a product, okay? So refer back to your answer to letter A. Aluminum ion is a product. We're going to be making more of it as the cell operates. Calculate the standard free energy of reaction. We're going to use that equation we just saw a moment ago. And we're going to plug in all of our values. Remember that little n is the number of electrons that you canceled out, which was 6. F is Faraday's constant. Multiply that times the cell potential, and I get approximately negative 700 kilojoules. Okay. When you plug all of the numbers in and you initially get a number for delta G, it will come out automatically in joules. I did not have to change my answer to kilojoules. That's just something that you can do if you wanted to. I could have left the answer as negative 7.00 times 10 to the 5th joules. That would have been fine. And again, guys, you can see that it is negative, which it should be. Last part, and this goes back to a previous subunit, is the value of the equilibrium constant greater than, less than, or equal to 1. Okay, and I said it's going to be greater than because the delta G value is negative. That indicates that this reaction favors the products. And of course, guys, you know, the equilibrium constant is a ratio of products over reactants. So if the numerator is larger, that's going to indicate greater than 1K. Okay, so now you guys have a much fuller picture of what's going on with a galvanic cell, and not only the concepts behind what's going on where, but also the math involved in calculating what kind of voltage these batteries are putting out. And I just want to say that, you know, in all of these calculations, these voltages that we've calculated have been really small numbers, like really, really tiny amounts of voltage. And you might say, well, you know, how does a battery ever power something like a car or something large? That's not enough voltage. And you're absolutely right. What they do is they take multiple galvanic cells and connect them in series or parallel sometimes. And you get a sort of larger total voltage by connecting them all together. So it's not just one galvanic cell, it's lots of galvanic cells being connected in series. Anyway, so I hope you have learned a little something today, and I look forward to seeing you next time.